Hello everyone, I'm Hinda Shabouni, Assistant Professor at CY Sergi Paris University, and I thank you for giving me this opportunity to present my experimental results carried out in Lerma Laboratory in France, the Laboratory of Studies of Radiation and Matter in Astrophysics and Atmosphere. So this presentation is about the hydrogenation of formic acid on cold dust grain analog surfaces. So we know that formic acid is the smallest and the simplest complex organic carboxylic acid containing 2 oxygen and 2 conformers related to the relative position of hydrogen atoms in the molecule with respect to Cu covalent bond. Where trans conformer is found to be more stable than 6 isomer according to ALMA observations in the gas phase. So bases in with its formate derivative formate group, formic acid is believed to be the most important precursor for the formation of more complex organic carboxylic acids and biomolecules used by life on Earth, including amino acids, glycine, protein, DNA bases. These potential bending blocks are important intermediates in chemical synthesis of probiotic species. Formic acid also plays a major role both in atmospheric and intestinal environment as well in biological fields. So formic acid is observed in in several environments in the interstellar medium. It is abundantly observed by radioastronomy in dense cold molecular clouds, a region for massive star formation, where the temperature of the gas and the dust is low and the density of molecules is high. In these environments, formic acid is also believed to be abundant in solid phase and mixed with other abundant astrophysical molecules, mainly methane, formaldehyde, methanol, CO, CO2. It is also observed in protoplanetary disks surrounding the protostars, together with the methanol and formaldehyde by ALMA observations in trans conformer. It is also observed found in a comet of planetary system, which are considered to be one of the most possible source for the extraterrestrial supply of organic material to the early Earth. It is, and recently an astrophysical group in Spain have revealed for the first time the possible detection of formic acid with other sulfur and nitrogen molecules in extragalactic sources, probably in a spiral arm of galaxy. These environments are dense in hydrogen molecule, warm, and dominated by shocks, intense UV, and the highest energetic X-ray radiations. So here in this slide, I will highlight the main gas surface processes which can occur in the prestellar regions during the early stages of star formation, and mainly in dense cold molecular clouds. In these environments, cold dust grain composite of carbonaceous material or silicates are covered with icy mantle, mainly composed of water and other molecules, methanol, methane, formic acid, CO, CO2, and these ices are exposed to gas phase bombardment of atomic and molecular hydrogen, leading to the formation of radicals which can diffuse on the surface and form new molecular species which can be condensed on the ice or dissolved into the gas phase, either by chemical desorption due to the high exothermicity of the reactions between the reactions at low surface temperature, or by thermal desorption due to the local heat of the grain by the infrared light coming from the nearest baby star or protostars. Icy mantle also are exposed to energetic particles like the UV photon, X-ray and cosmic radiations, and these energetic particles can induce radicals and complex organic species which can either remain on the ice or dissolve into the gas phase by non-thermal photo desorption process. In our laboratory, Lerma Sergia, we study mainly the chemical desorption and the thermal desorption. So here, in this slide, I will give the experimental methods used for our experiments. We use two cryogenic devices, formalism dedicated for the formation of molecules in the interstellar medium, and Venus for the formation of new complex organic molecules in the universe. The experiments are laboratory experiments were performed in the condition of the interstellar medium at low surface temperature, at low hydrogen fluxes, and at low surface coverages between 1 monolayer and 3 monolayer. Using three spectroscopic surface method, reflection absorption infrared spectroscopy, temperature programmed desorption mass spectrometry, and TP-dead temperature programmed during exposure desorption mass spectrometry. So here the laboratory, this is the experimental setup of formalism. It is composed of a magnet chamber, an ultra-high magnet chamber, where with a base pressure of 10 - 10 millibar. Inside the chamber, there is a sample holder simulating the dust grain, which is made with gold-plated copper block covered with graphite substrate and connected to a cryocooler to cool down the surface to 10 K. The main chamber is combined to two differentially pumping beam lines. One used for the introduction of the vapor pressure of formic acid, and the other is used for the deposition of hydrogen atoms inside the chamber. We use also the Fourier transform infrared spectrometer in the mid-infrared region by reflection absorption infrared spectroscopy with a grazing angle and with an external MCT detector cooled with nitrogen, liquid nitrogen. We use also a quadrupole mass spectrometer to detect species desorbing from the surface into the gas phase with their masses. We also use two substrates, highly oriented pyrolytic graphite and anamorphous water ice prepared by water vapor deposition at 110 K using a water vapor sprayer inside the main chamber. Here I will highlight the main result about the dimerization of formic acid on cold surfaces. So we use formalism setup and the TP-dead technique, which consists firstly to expose the sample of the sample holder made of graphite or water ice to the beam of ACOH, and while decreasing slowly the temperature of the surface from 120K to 1K using a heating rate of 00K 33 second minus 1. And we monitoring the species reflected from the surface during the exposure phase by QMS placed close to the surface in lower position at specific directions to collect the maximum of species desorbing from the surface during the exposure phase. And this figure shows the QMS signal in count by seconds of the ion fragments, so that cracking patterns of dimer given by mass 47 and monomer of ACOH given by mass 46 as a function of the exposure time of formic acids gases, and with the decrease of the temperature of the surface. So we see here that when at higher surface temperature, the impinging HCOH remain in the gas phase and did not stack on the surface. However, when we decrease the temperature of the surface from 150K to 100K, the signals of monomers decreases and that of the dimer increases, because some of monomers associate together on the surface, form dimers by hydrogen bondings and dissolve promptly into the gas phase at this range of temperature. As when we decrease the temperature below 100K, the gases of the introduced gases condensate, form dimers, and condensate on the surface and stay in the solid phase. So here I will give the main result about the reactivity of formic acids with H atoms, both on graphite and amorphous solid water ice. I will describe briefly the experiments. Firstly, we deposit, we expose the surface to the beams of HCOH and H atoms. The H atoms is prepared by microwave source discharge of hydrogen molecules. Then we apply the reflection absorption infrared spectroscopy with a grazing angle in order to identify the species formed on the surface by their vibrational signatures. After that, we apply the temperature programmed desorption technique by increasing linearly with the time the temperature of the surface from 10K to 220K using a quadrupole mass spectrometer to detect species desorbing from the surface into the gas phase. So here the results, the main results about the reactivity of HCOH with H on the graphite surface. In the left figure of press giving the variation of the absorbance as a function of the wave number, this figure shows two spectra. The black spectrum is that of HCOH deposited on graphite at 10K, and the red one is that of the HCOH plus H film deposited on HOPG at 10K. So we see here the small decrease of the main stretching absorption band of HCOH and a small the growth of small peaks of solid CO and H2CO, and that of probably water mixed with methanol and given by the absorption, large absorption band at 3,200 centimeter minus 1. After that, we apply the temperature programmed desorption for each film, and the other figure in the right gives the desorption rates in count by second as a function of the temperature of the surface from 20K to 220K. So we see this figure shows the desorption curves of the ion fragments or the new species detected by the QMS with their masses. We see here the small decrease of the monomer for mass 46 after H atom addition. We see also the growth of the desorption peaks of CO2 at 82K. We saw also the growth of the desorption peak at 143K, which may correspond to methanol, CO2, H2CO, water, and even at lower temperature at 45K, which may correspond to CO formed by the reaction. So the main species are CO-bearing species. Here in this slide, we show the main results of the reactivity of HCOH on the amorphous solid water ice. RES spectra shows here after H atom addition the broadening and the increasing of the main absorption band of HCOH, the growth of the absorption band of CO2 ice, and a large band at centered at about 2000 centimeter minus 1, which may correspond to the possible ionization of HCOH in a solid water ice matrix and not on the surface. TPD curves shows here the slow decrease of the monomer and the dimer of HCOH given by mass 46 and 47. The growth of desorption peaks of CO2 at 85K, which correlate with the RES observations, and we see also the growth of two double desorption peaks at higher temperature at 147K, which may correspond to the joules. So to understand the mechanism of the reactivity of HCOH on cold surfaces, we have built surface reaction routes taking into account the monomer of HCOH, the dimer of HCOH, and the different possible abstraction reaction of by the impinging H atoms coming from the beam. So here we saw that for the abstraction of the OH bound of the molecule with H atoms, we can form a water molecule mixed with the radical HCO, and its hydrogenation may form the CO-bearing species, H2CO, metal. The hydrogenation of this radical may form also CO by abstraction reaction, which can desorb into the gas phase by chemical desorption, according to some new publication in our laboratory. This first mechanism explains well our results in graphite substrate. However, the formation of CO2, which mainly observed on amorphous solid water ice, can be explained by the abstraction reaction of H atom either from the CH side of the molecule or OH side of the molecule by H atom. But these two reactions have high activation barriers. So we suggest that in our experiments, in our laboratory experiments, the abstraction reaction is mainly given occurs from the CO HC of bound of the dimer, followed by the breaking of two OH band, leading to the formation of H2, CO2, and two radicals of two complex organic radicals, which can be stabilized by the water ice environments, and their hydrogenation may form joules, which were observed in our experiments. We have also taken into account the reaction between CO, which can be formed by the reaction, and HCO on the surface. These species can form the intermediate HOCO, which can relax the intermediate HCO, which was not observed in our experiments, but has been identified by theoretical calculation on carbonaceous materials. These intermediates can relax and form CO2, can be hydrogenated and lead to the back formation of HCOH, CO2, CO, water, which can be added to the reaction products of formic acid with H atoms. So here I will see that our experimental results for the hydrogenation of formic acid with H atoms are important for the future observation by GWST. They are also important to further understand the chemistry in protoplanetary disk regions, where CO, Ci3OH, and formic acid are expected in the gas phase, are expected to be abundant in the mid-plane and the outer mid-plane protoplanetary disk regions, according to the new astrochemical models. These species are likely to be formed by hydrogenaceous surface reactions and then dissolve into the gas phase, either by chemical dissolption in the outer mid-plane disk cold regions at higher AV, and or by photoprocessing of ices in the mid-plane disk regions. These environments are birthplaces of comet and the planet formation regions. So here I will summarize the main results. Our experimental results show an efficient consumption of formic acid by H atoms on cold surfaces, and the formation of the products may depend strongly on the substrate, whether it is gold, whether it is graphite substrate or amorphous water ice. The difference in the product formation likely depends on the COH orientation in a specific direction, favoring or enabling either the H or OH surface abstraction reaction. We can suggest that in the case of graphite, the OH abstraction of the molecule is favorable because it can explain our observations for water formation and CO-bearing species, while in the case of amorphous solid water ice, the OH group can be engaged in by hydrogen bonding in the formation of dimer and other water molecules. So the abstraction reaction of H from the HCO bond seems to be more favorable and can explain the formation of the most important interstellar molecule CO2. So further experiments with the isotopic species rich in deuterium and on other surfaces, graphite, water, amorphous, crystalline, or silicates, are suggested to more understand the chemistry of carboxylic acids in cold environments. So I thank my colleagues in l'ERMA, Sergi, and the Programme National de Physique de Chimie du Milieu Interstellaire. And thank you for listening.